All right, kiddos, today we're going to talk about formal charge. Now, formal charge for some of you is probably something you've gone over before, but a little review never hurts. Remember that the idea behind formal charge is that you're saying what would be the charge on a given atom if the bonds were completely shared equally. Now, we, of course, know that bonds are not shared equally, right? That's sort of what electronegativity and polarity and all of that are about. But formal charge allows us to say, hey, this is what it would be if the way we've drawn it, we shared those bonds completely between each of these two things. Then what would be the charge on each of the individual atoms? Okay? Now here's why formal charge is really useful, because formal charge gives us a way to essentially pick between two equally valid Lewis structures, meaning that I had a molecule like carbon dioxide, okay? And you've probably seen that one drawn before, so you already know which one of these is correct. But if I drew that, each of these two models here is completely valid. In fact, some of you may remember when you were drawing covalent structures in your high school or your Chemistry 1 classes, that you draw a structure and your instructor would come around and say, yes, you followed the octet rule, but that structure is not the right one. And you were like, well, how am I supposed to know that? Well, the way that you're supposed to know that is from formal charge. So in other words, I've got carbon dioxide. These two are both legitimate ways that we could draw this, okay? There's 8 valence electrons here, 8 here, 8 here, 8, 8, and 8. Everybody has 8, so those seem like they would be two completely valid structures. And so we're going to talk about the rules of formal charge, and then how do we then distinguish between the two of them. Okay, so here's how formal charge works. Formal charge is equal to the number of valence electrons that atom would normally have. You looked at it on the periodic table, and you said, hey, carbon has 4 valence electrons. That's valence, okay? Minus how many electrons is that atom assigned in the molecule, given these two rules down here in pink on the bottom, okay? So you take the number of valence electrons that it would normally have, you subtract how many are assigned to it in the particular setup that you've drawn in your molecule, and then you give it a formal charge, okay? Many times that formal charge is going to be 0. Most of the time it's going to be 0. But sometimes it won't. Sometimes it's +1, sometimes it's -2, okay? And all of those things affect how we select which structure would be more appropriate. So let's run through this real quick, and we're going to assign a formal charge to each of our molecules here, or each of our atoms on each of these two versions here, just so you can sort of get a quick idea of how this works. So carbon, of course, normally has 4, right? So that all unshared electrons count as 1. I don't have any unshared electrons. All bonded electrons count as half. So how many assigned electrons does this carbon have? Well, 2, 4, 6, 8, but those are all bonded, so they count as half. So half of 8 is 4. It had 4 to begin with. I'm subtracting 4, and so that means the carbon has a formal charge of 0. Okay? So how about this oxygen over here? Well, oxygen, what's its normal valence? It's normally 6, right? Okay? So then how many does it have assigned in the molecule? Well, all unshared electrons are 1, so that gives me 6, right? 1, 2, 3, 4, 5, 6. Bonded electrons count as half, so that would be 2 electrons counting in the bond, but that only counts as half, so that's 1. Add that to the 6 I've already got, and I've got 6 valence minus 7 assigned, and so I've got a -1 on that oxygen. Okay? How about this oxygen? Well, again, oxygen typically has 6, right? That's its valence. How many is it assigned? 2. And then half of these bonded ones. So there's 2, 4, 6 electrons counted there. So that means 3 electrons plus the 2. That gives me 5. 6 minus 5 is going to give me a +1 over here. So my formal charges on each of these, I've got a -1 on this end, I've got a +1 on that end. Okay? Some students find it easier to say instead of all bonded electrons count as half is just to count each bond as 1 when you go up here to the assign. That'll get you to the same place. Okay, so let's go over to our other model then and see what we get there. So again, carbon's sort of in the same boat. It has 4 valence. It's assigned 4 in this case, so it's still 0. Our oxygens, they each have 6, and in fact, since they've got the same exact structure just on opposite sides, we really only have to do it once. So it has 6 valence. I've got 1, 2, 3, 4 unshared electrons, and then I've got 1, 2 bonds, okay? So that means it's assigned 6, it had 6, So the formal charge for each of these then is going to be 0. Okay? Now, here's where formal charge really matters, because what you want formal charge to do is essentially to tell you which one of those structures is more reasonable. So the one that's more reasonable is the one with the formal charges closest to 0. In other words, the ones without as many charges, that tends to be the Lewis structure that you want to pick. So when we draw carbon dioxide, we draw it like this. Now, there's other empirical data that goes in to show that that is correct, because we know that carbon dioxide is a non-polar molecule because of the symmetry that we've got going on here. If we had drawn it this way, that would in fact be quite a polar molecule. +1, -1 on the other side. That's absolutely polar. And of course, empirical data shows us that that's definitely not the case. So let's work one more example real quick just to make sure you've got a good handle on this. All right, so we're going to look at our thiocyanate ion. We're going to walk through, we're going to assign formal charges, because there are 3 ways that I could have drawn that out that made pretty good sense. And again, you might have been thinking there's probably more than that if you hadn't put carbon in the middle. Remember, sort of one of your rules for drawing stuff is carbon's typically in the middle, so we're going to sort of start there. Okay, so what now? How do we assign the formal charge? Well, I'm going to do the easy part first. Okay, so the easy part, at least to me, would be, let's look at the carbons in the middle. And each of the carbons is pretty much in the same scenario. It has 4 valence electrons to start with, and in each case, it's also assigned 4. Okay, so 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds. So that means in each of these cases, my carbon comes out to have a formal charge of 0. So that's pretty easy. So then that's obviously not going to be the deciding factor. The deciding factor then is going to be, hey, what's going on with the sulfurs and the nitrogens and all that stuff. So let's do formal charge for this sulfur. This sulfur is in the same group or same column as oxygen, so it normally has 6 valence electrons, and in this case it has 1, 2, 3, 4, 5, 6, right, if we're counting the bonds as 1. Remember, each bond is 2 electrons. Half of that is 1 electron, so we can just count each as 1. So 6 valence minus 6 that it has in this molecule, that gives us a 0. Nitrogen normally has 5 valence electrons, so 5 minus 1, 2, 3, 4, 5, 6. 5 minus 6 is going to give me a -1. Okay? We're going to jump over here to this one. Again, sulfur had 6, but in this case, it is assigned 5. And so that means I've got a +1 over here. Nitrogen has 5 valence electrons normally. It's assigned a share of 7. Okay, so 5 minus 7 gives me a -2. Okay, sorry I overlapped that. That's -2. In this case, sulfur normally has 6. It's assigned 7 in this case, so that means 6 minus 7 gives me a -1. Nitrogen typically has 5. Again, it is given a case of where it's got 5 assigned to it, so that means that that also has a formal charge of 0. So we've assigned formal charge to everything. We can sort of immediately say, hey, this is not the one that we want. Okay, why is that? Well, because the formal charges are way away from 0, right? In each of the other ones, I have a formal charge of a negative on each one, so everything's not 0. But I don't have any like 2s, 3s, all of that stuff. So that one's pretty much automatically out. I got to pick one of these two. And by the way, when we're doing a polyatomic ion or anything that's charged, as it is in this case, the formal charges better add up to the charge that you have there. If it doesn't, then you did something wrong. You forgot to put an electron in your Lewis structures. You're like, we didn't do that in CO2. There was, we had a 0, 0, 0. Yeah, CO2 isn't a charged molecule, okay? So therefore, there wasn't going to be a formal charge probably on the correct structure, or they were going to balance out. So in each of these two cases, I have a -1 on one of the molecules, okay? So we cross that one out. It comes down to, is it this one or is it this one? Well, this is where you have to apply some other sort of logic, common chemistry sense, which is, if there's going to be a negative charge, it kind of makes more sense that the negative charge would be on the most electronegative of the elements, okay? So is nitrogen more electronegative or is sulfur more electronegative? Well, nitrogen is, okay? So that means that it makes good sense that the negative formal charge is going to be on the nitrogen as opposed to it being over here on the sulfur. which means that this is our correct structure. Okay? So remember, kiddos, formal charge is the number of valence electrons, what you would find normally on the periodic table, the Lewis dot structure electrons that you would normally put on there, minus how many electrons are assigned to it in the given structure that you've drawn, counting these two rules. Unshared electrons count as 1, bonded electrons count as half, or you can say each bond counts as 1 individually. Okay? Subtract those, put the charge on each atom. All right? Thanks, kiddos.